we're going to simulate the internal parts, the column environment of a distillation system, and then also see how heat integration can be done using UNISIM. This is actually a basic heat integration process. Then we're going to see whether it actually leads to reduction in operating costs, particularly energy demands. So what we're going to be doing today, we'll have this default column on your right, as you can see. So maybe I can show so this is actually the default column from the right. So we have the normal column, 8 stages, and then we have the condenser and then the reboiler. So we're going to change from this oversimplification of the normal of the distillation column, and then we're going to take it into more of a real life operations. So we have a heat exchanger instead of an electric cooling condenser, an electric cooler, or a kettle reboiler. So we're going to use the cold stream, then we're going to cool our condenser stream, then we're going to pump, and then have an external electric boiler to raise that temperature to maintain the utility stream that will be supplied to the reboiler. So this is actually the case study, so you can understand that. So for this process, we're going to have a 350 kg per hour benzene toluene mixture. So it's actually an equimolar mixture, 0.5, 0.5. The feed condition is actually 1.1 atmosphere and 25 degrees. So an 8-stage distillation column, so pardon me. An 8-stage distillation column, we're assuming we have 0 pressure drop across our column. So the optimal feed location is 4, and then the design specification, so we need product purities of 90% for both the bottom and the top stream. And we have an access to about 700 kg per hour steam utility at 3 atmosphere and 300 degrees, as well as access to cooling water at 1 atmosphere and 25 degrees. So we're going to assume we have access to the same mass of cooling stream and heating stream. The optimization engineer proposes that the condenser in this case is actually a total condenser. So instead of that rejected energy, we can use that to offset the energy demand for our boiler. They are going to solve and find the amount of electrical energy that will be needed to maintain this utility supply to the column. We're going to use Ben Robinson as the fluid package, so I think we should start. So this is actually my UNISIM design. I'm going to set up a new case, and I'm going to add my component list. So I'm going to add benzene, toluene, and water because it's actually what I'm going to use. And water. And so I'm going to add a fluid package to the component list, and going to use equation of state, Ben Robinson. So just check if your binary coefficients are all there, all present. So I'm going to enter my simulation environment, and I'm going to have my feed distillate the bottoms, and I'm going to add my condenser energy and my reboiler energy, and I'm going to add my regress distillation column. So it takes a while, so I'm going to give it some few seconds. So we have 350 kg per hour of benzene, so 0.5 mole fraction benzene toluene mixture. So I'm going to so there it is. So I'm going to define my feed first. And then temperature is 25, 1.1 atmosphere. So This should be 1.1 atmosphere. And the mass flow, 3. I think it's actually 350 kilogram per hour. So I'm going to specify 0.5 and 0.5 mole fraction. Okay. So the feed is actually specified. And I'm going to specify the number of stages I have, 8. And stream, feed, 4th stage, condenser energy. Then my reboiling agent, so total condenser. And then I have the product streams. And then next, and then I'm going to specify the condenser pressure because I'm assuming I'm having 0 pressure drop. So I'm going to assume it's actually 1 atmosphere. So I'm going to click next, and then next, and then done. So I'm not going to specify that part. So monitor your specification. So reflux ratio, distillate rate. So I'm going to deactivate those, and I'm going to add my feed specifications as my design objectives for the distillation column. So I'm going to add column component fraction, and the stage is the condenser, and benzene is actually the lighter component. So I'm going to specify 0.9 for benzene, and I'm also going to add the column component fraction. Then the reboiler stage, so I'm going to set toluene at 0.9 also. So my degrees of freedom 0, so run, the column has already converged. You can see my profiles. And then I'm going to enter, I'm going to change my solver first. I'm going to modify the inside out so that I can add the heat exchanger inside the column environment. So I'm going to enlarge that image. And I'm going now to try and understand what this part means. So we have the top part and the bottom part. So we have a total condenser. Now total condenser is actually made up of a cooler. So I'm going to see. So I'm going to try and model this part so you understand how it behaves. So I'm going to take a material stream, and I'm going to add, and then a cooler. That energy that has to be drawn from the stream, the product, and then I'm going to add a stream splitter, and then I'm going to have 2 product streams emerging from this. So this is actually what the condenser is made up of. So if I specify my stream 1, if I define from another stream to condenser, so it should have the same composition, same temperature, pressure profile, as that is what is going to into the condenser, and I'm going to set as my inlet to the heat exchanger, and then my energy stream should be Q102, and so I'm going to set my stream 4 here as the outlet. Parameters, so delta P, pressure drop 0, okay, in that. So the inlet to the stream splitter is stream 4. Then the outlet will be stream 5 and stream 6. So I'm going to run the column. I just need to get some values from the top. So if I run, then I need to specify the amount of energy that has to be drawn from a condenser, or I can specify the stream 4 from stream 2, the composition. It can work as well. That's a total condenser, so I can specify the vapor phase fraction here to be 0. So it works as well. Then I have my temperature as 82.03. So I have so many ways to define this more of a modular design of trying to integrate it into the original column. I can also specify the amount of heat to be transferred to the cooler as the same as that was being transferred to from the condenser. I can also delete this specification, and I'm going to do with temperature 82.03, and so it has to be the same. And if you check the amount of heat transferred from the cooler, it's actually 1.503, and same as that was actually to the condenser. This is actually what happens. Now I have two streams here. Stream 5, if I rename this reflux, so the split ratio will be specified depending on my the reflux ratio that I specified in the column, or I can specify the distillate flow rate from stream that I desire. So in this case, the distillate flow rate was actually 163.5. So if I take my stream 6 to be my distillate, then I should have 163.5. So I'm going to rename this as distillate. So we have mass flow should be 163.5. So this is actually what happens. This is actually another simplification to what is portrayed initially. And if you do a quick stream comparison between distillate and stream 2, you'll find that the composition have to be the same: 0.9, 0.9, and 0.1. Okay. Now, this is actually what happens, but instead of having an electric cooler, we use a cooling utility, and then we have a heat exchanger. So I'm going to add a heat exchanger, transform change icon. I'm going to do this. Then I'm going to have this material stream. That's actually the cooling water stream. So I'm going to rename this part cooling water stream, and we know we had access to cooling stream of 25 and 1 atmosphere. The mass flow is 700 kilogram per hour. I believe the molar flow is actually 1 for pure water. So normalize, then okay. So that first part has already been calculated. So we are going to connect it into our heat exchanger. So that is cooling water as my inlet. Then my outlet will be stream 6. Then I'm going to delete the heat exchanger, the heat exchanger, the cooler. Then I'm going to delete the Q102. And I'm going to add stream 1, and the outlet should be stream 4. Okay. Now, so pardon me a little, let me drag and drop this here. Okay, let me just transform that. I'm going to mirror it about Y. Then I'm going to rotate it by 90 degrees. Yeah. So that works. Now I have to set my pressure drops to be 0, then also that 0. As you can see, it has converged. Let me try to arrange this a little better. Okay. Now I can delete this. No, before I delete this part, I'm going to delete my specification here parameter for the distillate. That was actually my split. So I'm going to delete that part, and then I'm going to add it into my main column specification. And then I'm going to delete the condenser part, and I'm going to take stream 1, I'm going to delete that. And so I have the same to condenser stream actually as my inlet to that side. So it adds that specification, the temperature specification. And I'm going to delete this reflux part. I'm going to use, that was the original one, then that is that reflux, and then the distillate at that point. So if I run my column, so there's not. So I'm going to set my specification first. So I'm going to take the distillate rate, and then I'm going to view that. But so it's actually stream related. So it should be distillate stream. So let me do that again quick. So it's actually on the distillate stream mass basis. So 163.5 kilogram per hour. And then I'm going to now set my column top pressure. So at that point it's 101.325, sorry, kilopascal. So if you run that part, okay, specification again. So I didn't click on active. Okay, and if you run, so it has converted. So the first part has been solved. So now let's do the bottom part of the column. So we're going to do the same thing. So I'm going to take heat exchanger. I'm going to drag and drop it here. I'm going to transform the image. I like how this depicts the heat exchanger. I'm going to take my heating string. So this is actually the heating utility. So this is utility at a pressure temperature of 300 degrees and 3 atmospheres actually. That's my outlet temperature. So the mass flow is the same, 700 kilogram per hour. Pure water stream, so that is one. Okay. Now we also have that the outlet after the utility has transferred its latent energy. That will be stream 1. Okay, so I'm going to add these two other streams here. So let me run the column first. And then I'm going to define stream 5 as that, same as that reboiler stream. Okay, and that will be my shell side inlet. And stream 7 will be the shell side outlet. And so we further analyzed and we saw that the reboiler acts as another stage. So it's actually an additional stage because the first stop, the top part we had a total condenser. So there was no need for a two-phase separator. It was a total, so we had one phase. Now, let me just show you something real quick. Okay, just before that I'm going to deactivate this heat balance added automatically after adding the heat exchanger. And so if you take a good look at your boiler composition, so you find it actually has high benzene concentration than the reboiler part. This is actually as a result of the heat added to your kettle reboiler here. So the heat added vaporizes the more volatile component that is actually benzene. So it concentrates benzene. So it removes the mass of benzene from this liquid phase stream. So we have more concentrated toluene stream here. So this is actually more of a stage compared to our condenser, because if you take a good look at your condenser stream, so you see the composition, sorry, pardon me, so you see the composition 0.89, approximately 0.9 and toluene 0.1. It's actually the same after exiting your condenser. It's actually the same, so it has that of the reflux because it's a total condenser. So it does not add or change the composition of your products, while the reboiler here does change your composition. So this is actually another stage, can be viewed as another stage in this column. So we're going to add a two-phase separator. But before we add that two-phase separator, we also have to completely specify our design of our heat exchanger. And so we see that the outlets of that heat exchanger from stream 5 we have stream 7. So we're going to define stream 7 temperature as the same as that of the product, because it's actually assumed to be isothermal 105.3. So I'm going to do 105.3 as my design specification for that heat exchanger. And so if I run, the column should run. Okay, let me do this heat balance. It's actually added automatically each time I add a heat exchanger. So we have specified that column, and then the parameters is the pressure drop for my column. My heat exchanger should be 0. So that heat exchanger also has converged. So stream 7 should have the same composition as my after reboiler the column. So okay. So I'm going to now take that stream 7 as the inlet to the two-phase separating column, and we'll have stream 8 as the vapor outlet, and stream 9 as the liquid. Okay, so we see that part. So I'm going to transform this. About that. No, sorry. Yeah. So I'm transforming it again about twice. I'm going to reflect it this side. So let's set it a bit more cleanly. Now, so stream 9 is my bottom, should have the same stream specification as my design specification 0.9 and 0.1, so that's actually done. Now we have to delete this part, the reboiler part, and then this stream. And I'm going to delete stream 5, and I'm going to add to reboiler as that stream inlet. Okay, and stream 8 should be to the boil up. So delete that and then add boil up. That part. So go back to your column, so specify your pressure at the bottom of your column should be 1.325. Then run your column. So it has converged. So this is actually what was required in the simulation aspect of it, but you also have now to set up stream 6. It's actually pure water, so we now have to preheat. Sorry. So we're going to preheat. Now we're going to set up the utility support structure to raise now the temperature of our preheated steam from this actually preheated water from the cooling from the condenser, what used to be the condenser. So I'm going to add a pump first and then a heater. And I'm going to add a heater, an electric heater. And then the outlet should be the utility stream needed for the reboiler at the bottom, so that's okay. The energy should be Q102, the inlet should be stream 3. Again, the pressure drop should be 0. Okay. And the pump inlet should be stream 1. Outlet should be stream 3. The energy should be Q11. Then remember the parameters, I'll just specify. Sorry, what the inlet should be stream 6. So my 3 bars, 3 atmospheres, so not, 3 atmospheres. So I'm going to delete parameters, okay. So I'm going to solve the column. So it has converged, and this is actually a support utility system. Now, the amount of energy that will now be needed to to maintain this utility system is actually 1.942 times 10 power 6 kilojoules per hour of electrical energy. So if I go back to my parent simulation environment, so assuming that there was no heat integration done, then obviously the pump will require the same amount of energy as what is being required after the heat integration, but the amount of electrical energy that will be needed will be, we should see a reduction. So we're trying to quantify the amount of electrical energy savings that this system will incorporate. The outlet should be stream for the energy stream. The inlet should be stream for the energy should be stream. The outlet should be stream 5. So remember, so my pressure drop 0, but my temperature should be 300. 300 and 3 bars, 3 atmospheres. So again, so stream 1 is actually at 25 degrees, the pressure of 1 atmosphere. Mass flow is 700, and then pure water stream. Okay. So you can see this original system, if we were to maintain that utility, we'll need about 2.092 times 10 power 6 electrical energy needed to heat my cooling water to be able to maintain that utility system. Okay, but inside the column and environment, so they're actually seeing a reduction to about 1.92. 1.942 times 10 power 6 kilojoules per hour of electrical energy saving. So the difference is what was required to solve the question successfully. So that will be all. So if you think you learned something from this video, you can comment and like and share. That will be all. See you again in my next video. Thank you.